This video is about chromatography. The learning outcomes for this clip are: you should know that the gas-liquid chromatography can be used to separate mixtures of volatile liquids, and know that separation by column chromatography depends on the balance between the solubility in the moving phase or mobile phase and the retention in the stationary phase. The retention in the stationary phase really means how well the chemical binds to the surface of the stationary phase. So there's three types of chromatography to be aware of: paper chromatography, which you learnt about in Year 7, column chromatography, and also gas-liquid chromatography. So we'll set the scene with paper chromatography first, so you get an understanding of what the other concepts are about. So with paper chromatography you have a stationary phase, which is the paper. You have the mobile phase, which is the solvent. You have the sample, which is a spot, let's say a pen, which has different dyes in it, and these dyes are separated. And they are separated because the dyes within the spot have different solubilities in the mobile phase. And so some of this is actually a brown spot there. Let's say the brown spot has a high affinity for the stationary phase, the paper, so hooks onto the paper very easily, and so doesn't travel very far. The red spot, though, travels much further because it has a much greater affinity for the solvent phase, which is moving up the paper. So what we think about now is how the column chromatography works. So column chromatography is where you have a different system going on, and in fact the solvent runs downwards rather than upwards. So it runs this way, the solvent runs this way rather than upwards. So what we have is a dye, let's say it's a green dye which is made of blue and yellow. And we want to separate the blue and the yellow, so we use a solvent in the column chromatography to do that. So the yellow dye has a greater affinity for the mobile phase. That means it is more soluble in the mobile phase. And you can start to see that as we put more and more solvent down here, the yellow dye can move more quickly down the column, whereas the blue one takes longer to get down there because it doesn't bind so well to it. Perhaps its intermolecular forces are weaker with the mobile phase. And so after several frames we carry on adding the solvent. So eventually in frame 4 the yellow dye has been collected in the beaker, and the blue dye has not been collected yet. We could carry on perhaps another 2 or 3 frames, and eventually we would collect the blue dye. So what can this can be used for separating different types of molecules, not just dyes. It could be used to actually separate amino acids, because amino acids would actually have different solubilities in the different solvent phase and in the stationary phase. So some dyes that the blue dye has a stronger attraction to the stationary phase, hence it moves more slowly. So generally the separation of a chemical depends on a couple of things. Firstly, the solubility in the mobile phase, and secondly, the attraction of the dye or substance to the stationary phase. So the last one is to look at gas-liquid chromatography. This can be used to link crude oil pollution to tankers. It could test athletes' blood for drug taking, and it can also identify amino acids. So this is how it works. We have a mobile phase, which is inert helium gas, so it doesn't react with the sample. It would be useless using, for example, oxygen, because it could actually react with samples we are testing. We inject the sample in here. There's a capillary column which is lined with brick and also oil. Then there is a detector which picks up the different samples that are detected as the chemicals come out, and then there's a reading printout. Let's have a look at the printout. A phrase I haven't used yet is something called the retention time. So many chemicals might have a short retention time, and that would be, say, this amino acid. So we have the time taken along the x-axis. We have the amounts of substance on the y, so it actually tells us how much of each chemical is actually present in the mixture. So let's say we got this is a mixture of amino acids. They've been separated. So some amino acids would have in this sample have a small amount, a trace amount, and then amino acids C and D, because they have got the greatest peak. That means it's the most common in this particular sample. Amino acid A, I've labelled it, is detected most quickly, so it has it's got a greater affinity for the mobile phase, so it moves through the gas chromatography machine most quickly. And B, amino acid, has taken ages to get through the machine, so because it has a higher affinity for the stationary phase, that is the brick and the oil. So we can analyse amino acids present in a sample, and the large amounts are in green. We could also check to see which oil sample we might have. Let's say there's been an oil slick and we want to blame a particular company or tanker on this slick and prosecute. We can analyse the sample by again using gas liquid chromatography. So again, we've got time on the x-axis and we have the amounts on the y-axis. And so different samples of oil from around the world would have different amounts of different alkane chains. So in this particular sample, we've got octane, nonane, decane, undecane, etc. And let's say it's Saudi Arabia, they might have a higher level of octane and a lower level of N-decane. Then it's very unique for each part of the world. So the pentadecane has got the longest chain length. It's 15 carbons, so it would have the strongest intermolecular force to the stationary phase, so it moves through most slowly. And octane has the shortest chain because it has the weakest intermolecular forces with the oil in the capillary tube, and so it will move very quickly through the machine. So what we can do is we can link up the crude oil pollution found on the beaches that we find, and we can get an exact match with a database of different samples around the world, and then we can prosecute. So to sum up, key points of GLC: we've got a mobile phase, which is the inert carrier gas. We've got the stationary phase, which is a powder or a brick coated with oil, and we have the retention time, which is how long it takes for a particular sample to move through the system, and they move through the system depending upon how well they bind to the stationary phase, or how well they bind onto the mobile phase. And we talk about the affinity of this.